We take nylon for granted now, don't we? I mean, it burst onto the scene in 1939, this completely new synthetic fiber.
Totally revolutionary then.
And now it's just, well, it's everywhere. Socks, carpets, car parts, all that stuff.
It's a real workhorse.
And you, our listener, you sent over this really fascinating research paper. It digs into a pretty specific question. Dyeing nylon. But not with the usual dyes.
Right. It's looking at direct dyes, the kind you'd normally use for, say, cotton or linen.
Plant-based stuff.
Exactly. And the big question is, can we actually use these effectively on nylon? And, crucially, can mordants help?
Okay, so let's unpack that a bit. Direct dyes, the paper reminds us they came about, what, early 20th century?
Yeah, around then. And their big advantage was they were easy to use on those cellulosic fibers, like cotton.
Simple process.
But the downside is the bonds they form aren't always super strong. They don't always, stick that well long term.
Right, less permanent.
That's the issue. And that's where mordants potentially come in.
The helpers?
Exactly. Think of them like a primer or a fixing agent, often metallic salts. People have used them for ages, especially with natural dyes.
To make the color grab on better.
Yeah.
And stay put.
Precisely. The word mordant actually comes from Latin. Mordere means to bite.
Huh. Okay. Like they help the dye bite into the fiber.
That's the idea. Give it a better grip.
So your mission, listener, was to figure out if these mordants could give direct dyes a better bite on nylon specifically.
Yep. Looking at how much dye the nylon absorbs, that's exhaustion. How well it stays there after washing and stuff, that's fixation.
Right.
And, of course, the final color quality, how it looks, how strong it is.
And this research used quite a few, didn't it? 9 mordants.
That's right. 8 metallic ones, things like alum, copper sulfate, zinc sulfate, familiar names in dyeing.
And 1 bio-based one.
Tannic acid. Plus, they also looked at gallic acid and ascorbic acid, which popped up in some key results, and 4 different direct dyes: red, blue, yellow, black.
Okay, so before we dive into the results, maybe a quick refresher on nylon itself. The paper mentions nylon 6 specifically.
Right. It has a more, let's say, compact molecular structure compared to nylon 6. Tightly packed.
A bit more dense.
And chemically, nylon has these N groups, amino groups, and carboxylic acid groups.
Okay.
And those groups are what make it receptive to certain dyes. Acid dyes are the most common choice for nylon.
Why is that?
Because acid dyes form strong ionic bonds, like a chemical attraction, with those amino groups in the nylon. Very effective.
Gotcha. But this research is looking beyond acid dyes.
Exactly. It's exploring these direct dyes, which are chemically quite different. They're anionic, negatively charged.
And designed for cellulose, like we said.
Right. They're usually long, flat molecules with sulfonate groups. They stick to cotton mostly through weaker forces, like hydrogen bonds, not the strong ionic link you get with acid dyes on nylon.
And they tend to clump together in water.
They do, yeah. Aggregation, that's another characteristic.
So not a natural fit for nylon, chemically speaking.
Not really. And typically with direct dyes on cotton, you get decent light resistance, but poor wash resistance unless you add another fixing agent.
Okay. And the paper points out there isn't much research on using these direct dyes on nylon.
Relatively little compared to acid dyes or reactive dyes on nylon. That's what makes this interesting. People haven't explored this combination as much.
So this study tried bridging that gap using mordants. How did they apply them?
They tested 3 main methods. First, pre-mordanting. Treat the nylon with the mordant before you add the dye.
Okay, prep the fabric first.
Second, metamordanting. Put the mordant and the dye in the dye bath together with the nylon.
All in one go.
And third, post-mordanting. Dye the nylon first, then treat it with the mordant.
Dye first, fix after.
Yeah.
Got it. And the list of mordants was pretty varied.
Yeah, we mentioned alum, copper sulfate, zinc sulfate, also calcium carbonate, ferrous sulfate, that's iron magnesium sulfate, and the biomordant, tannic acid. Plus, gallic and ascorbic acid showed up significantly.
How do these mordants actually help, theoretically?
Well, the papers suggest, particularly with metal mordants in acidic conditions, the metal ion could act as a bridge.
A bridge between?
Between the negatively charged dye molecule and potentially the nylon fiber itself. Metal ions can accept electrons, forming a kind of complex that links the dye to the fiber more strongly.
Ah, okay. Like a connector piece.
Sort of, yeah. Hopefully improving both uptake and how well it stays fixed.
So the aim was better dyeing, better color, better fastness, how well it holds up.
Exactly. And this was kind of novel because apparently earlier tries using metallic mordants with direct dyes on nylon weren't very successful.
So they were hoping to find the right conditions, the right combinations this time.
Precisely. Find combinations that actually work.
All right, let's get into the results then. What did they find? Starting with the red dye, CI, Direct Red 23.
Okay, for the red dye, generally adding a mordant did help. It tended to improve the exhaustion, how much dye went onto the fabric, and the fixation, how much stayed there. Overall dyeing was better with mordants.
Any standouts for the red dye?
Yes, this was really interesting. When they used pre-mordanting gallic acid and ascorbic acid, those plant-derived ones gave the best results.
Really? Better than the metals?
For red, yes. Highest color strength, KS value, best exhaustion, and best overall fixation. Alum showed good fixation in pre-mordanting, but less dye actually got onto the fabric.
What about the other methods for red?
Metamordanting, applying them together again, gallic acid, ascorbic acid, and also copper sulfate, did well for exhaustion and overall fixation.
And post-mordanting, dyeing first.
Gallic acid, ascorbic acid, and this time tannic acid performed well, though they noted fixation was sometimes a bit lower with post-mordanting for red.
Why might that be?
They speculated maybe the dye-mordant complex was forming more on the surface, not getting as deep into the fiber when applied afterwards.
Okay, so for red, those biocompounds were surprisingly effective.
Yeah, gallic and ascorbic acid really shone with the red dye across the board.
Fascinating. Okay, what about the blue dye, CI, Direct Blue 74?
Big difference here. Without any mordant, the blue dye barely worked at all. Very poor exhaustion and fixation, basically no color.
So mordants were essential for blue.
Pretty much. And with pre-mordanting, zinc sulfate and ferrous sulfate, the iron one worked really well. High exhaustion, high fixation, good overall result.
Any that didn't work well for pre-treating blue?
Yeah, calcium carbonate and magnesium sulfate didn't do much good in pre-mordanting for blue.
How about meta and post-mordanting for blue?
For metamordanting, putting them in together, zinc sulfate was the best. Gallic acid, ferrous sulfate, and copper sulfate also gave good uptake and fixation, but the final color wasn't as strong after washing.
Suggesting surface dyeing again.
Possibly, yeah. Lower KS2 values, which relate to color strength after washing. For post-mordanting, copper sulfate showed high exhaustion and overall fixation. Tannic acid, though, didn't work well as a post-mordant for blue.
So for blue, it was more about specific metals.
It seems like zinc sulfate, ferrous sulfate, and copper sulfate were the more consistent performers for the blue dye.
Okay, moving on to the yellow direct dye. This one didn't have a CI name mentioned.
No, which is a bit unusual. For yellow, they actually got moderate results even without a mordant. Some uptake, some fixation.
But could mordants improve it?
Generally, pre-mordanting seemed the best approach. Zinc sulfate and ascorbic acid were interesting here. They got 100% exhaustion, meaning all the dye left the water.
Wow.
But the fixation was only moderate, again, maybe forming a complex on the surface rather than deep within. Magnesium sulfate also did well in pre-mordanting for yellow.
And the other methods for yellow.
Metamordanting, applying together gallic acid and ascorbic acid, gave strong color. And interestingly, gallic acid seemed to penetrate better in metamordanting compared to pre-mordanting for yellow. Post-mordanting with ferrous sulfate gave the strongest yellow color, paradoxically, even though the exhaustion and overall fixation were low, suggests a very strong complex, but maybe just on the surface. Magnesium sulfate was poor for post-mordanting yellow.
So for yellow, which mordants looked most promising overall?
They highlighted zinc sulfate, ferrous sulfate, and copper sulfate as potentially better matches, with copper sulfate tending to give higher fixation.
All right, last one. The black direct dye, CI Direct Black 22.
Okay, black also showed moderate dyeing without a mordant, similar to yellow in that regard.
And with pre-mordanting.
Mixed results. Zinc sulfate and copper sulfate gave high exhaustion and overall fixation, but the final black color wasn't very intense, a bit weak. Whereas calcium carbonate and magnesium sulfate gave a much darker black, high KS and good fixation, but less dye was actually absorbed overall. And gallic and ascorbic acids, they didn't work well as pre-mordants for black at all.
Interesting contrast to the red dye results. What about meta and post for black?
Metamordanting with calcium carbonate and magnesium sulfate was good high exhaustion, fixation, overall fixation, and strong color. Copper sulfate gave high exhaustion, but less fixation and weaker color. Alum was poor here.
Okay.
But post-mordanting dyeing first, then adding the mordant, that was the winner for black.
Really, across the board.
Pretty much, yeah. It gave the most consistent and best results across almost all the mordants tested. High exhaustion, high fixation, high overall fixation, and strong color strength. Alum and ferrous dissecous sulfate were particularly good as post-mordants for black.
So post-mordanting is the way to go for this specific black dye.
It certainly seems the most suitable method based on this study, using these mordants. And calcium carbonate showed really impressive fixation levels with black in both meta and post-mordanting.
Wow, it's amazing how different the best approach is for each color. Pre for yellow, maybe some biomordants for red, specific metals for blue, and post for black.
It really highlights the specificity of these interactions. Dye structure, mordant type, application method, it all matters.
So beyond just getting the color on, they also tested how well it stayed there, right? Color difference, DE?
Exactly. They measured the color change after 3 things. An extraction test using pyridine, a standard wash test, and exposure to light. Higher DE means more color change.
Which test caused the biggest change?
Generally, the pyridine extraction test. It's quite harsh.
Okay. What were the main findings there?
Yellow dye changed the most after extraction. Black changed the least.
Even if it was well fixed initially?
Yes, because DE measures overall color change, including shifts in hue or brightness, not just loss of dye. High fixation didn't always mean low DE. Black's stability was probably helped by it being, well, black close to neutral gray, fewer dimensions for color shift.
Any patterns with the methods?
For red dye, post-mordanting often led to higher DE after extraction. For blue, meta-mordanting seemed a bit better in resisting extraction changes.
Okay, and wash fastness. How do they hold up to washing?
Black dye was the best again, especially when post-mordanted. Yellow was generally the poorest wash fastness.
Any specific mordants that helped with wash fastness?
For red, ascorbic acid, calcium carbonate, and zinc sulfate looked good. For blue, gallic acid helped when used in pre-mordanting. For yellow, ferrous dissecans, sulfate, and copper sulfate helped minimize color intensity changes after washing. And for black, calcium carbonate, again, showed good wash fastness.
And finally, light fastness. Resistance to fading.
Bit of a mixed bag here, too. For red, pre-mordanting with zinc sulfate, gallic acid, ferrous dissected sulfate, or copper sulfate gave the best light fastness.
Oh, okay.
For blue, the worst fading happened with calcium carbonate, magnesium sulfate, and ascorbic acid. Gallic acid, however, was good for blue's light fastness in both pre- and post-mordanting. Zinc, ferrous, and copper sulfates were generally good for blue's light fastness, too.
Interesting.
Tannic acid seemed to help the yellow dye's light fastness. Copper sulfate was good for blue, red, and black light fastness, but actually poor for yellow.
So copper sulfate helped 3 out of 4.
Right. And again, the initial dyeing results, exhaustion and fixation, didn't always predict the light fastness. It's a separate property.
So let's try to wrap this up. What's the main takeaway from all this complex data?
I think the biggest point is, yes, you can use these mordants, including common metallic ones, to help direct dyes work on nylon. It's possible, but it's definitely not simple. Success hinges massively on the specific dye you choose, the specific mordant you pair it with, and how you apply it pre, meta, or post-mordanting.
No silver bullet. No single mordant or method work perfectly for all colors.
Not at all. It's very much a matching game. We saw gallic and ascorbic acids showing real promise for that red dye. Certain metals like zinc, ferrous, and copper sulfate seemed better suited for the blue dye.
Right.
And the black dye really seemed to prefer post-mordanting across many different mordants, with calcium carbonate offering excellent fixation.
And the fastness results were complicated too.
Yeah, wash and light fastness don't just depend on how much dye stuck initially. Changes in the color character itself, the chroma or hue, are a big factor in that DE value. And it seems the inherent color of some mordants might also play a role. You know, ferrous sulfate can be yellowish, copper sulfate bluish.
That makes sense.
The black dye was maybe the most straightforward case, where the initial uptake and fixation seemed to relate more clearly to its good wash fastness.
So essentially, this research opens a door. It shows there's potential for using direct dyes on nylon with mordants, giving alternatives to just using acid dyes.
Exactly. It opens possibilities. But it also underscores that you need to be really selective and do your homework, or rather your lab work, to find the right combination.
The complexity is kind of the surprising part, isn't it? How differently things behave.
Absolutely. And this work lays a great foundation. You could see follow-up studies looking at different concentrations, maybe other direct dyes, other mordants. Lots more to explore.
Definitely. And it leaves you, the listener, with something to think about too, doesn't it? Beyond just the color science.
How might these findings connect to the push for more sustainable dyeing?
Right. Different mordants have different environmental profiles. Alum is different from copper sulfate, which is different from tannic acid.
So it becomes a balancing act, doesn't it?
Huh.
How do you weigh the color quality, the fastness, the cost against the ecological impact of the specific mordant and process you choose?
Lots to consider. Definitely something for you to mull over.